So in this lecture we are going to talk about vectors. We are going to distinguish vectors from other similar topics that you see in mathematics or in applications in physics. One of those words that are used in competition with vectors are called scalars. We have already seen matrices. Let's write just some mathematical representations of these things. So a vector could be a row of numbers such as this, or a column of numbers such as a scalar is just a single number. Say 11. A matrix connotation is that you typically have a rectangular array of numbers. Now, in applications, we said quantities that are shown have properties of vectors are things such as velocity, acceleration, and any kind of a concept that is tied to these things. For example, in physics, if you have come across the concept of momentum, you know momentum. What is momentum? Mass times velocity. If you have mass, you multiply it by velocity, you get something you call a momentum. And a variety of items that are derived from these quantities could be vectors. You go to electricity and magnetism. Well, of course, we have the concept of force. That's still in mechanics, so forces are vectors. And then in electricity and magnetism, we said the current as well as electric field is electric intensity is a vector. Magnetic fields are also made of so a concept of a field simply means having lots of vectors in one place. So let me just characterize this thing. Scalars, things such as mass is shown by just a single number, doesn't have a sense of direction attached to it. Matrices, we saw many examples of matrices arising from a variety of equations before. Okay, now let's go ahead and see, well, in these applications of vectors in physics, what is it that we expect from them? Let's go ahead and explain particularities of vectors. Suppose that you are on say a boat, and you have a certain velocity with respect to the water that's just right behind you, below you. So here's the lake. So you row your boat, or you have a sail or something, and with respect to the water that is around you, you are going at a certain speed in a certain direction. So you will have a velocity. So this is velocity of boat with respect to water. Now, sometimes your boat falls in a current. That is, the water in the lake itself isn't just sitting there, but perhaps there is a stream in it. There's a jet stream or something that water could be flowing in a certain direction. Okay. So the water itself has perhaps some velocity with respect to the shoreline. So here's the shoreline. And that body of water itself could be moving. So this is velocity of the water that's underneath you with respect to, I'm going to abbreviate, with respect to the shoreline, or with respect to land. Now, typically, you might be interested in your situation with respect to land. That is, well, in which direction am I moving with respect to the shoreline there? So we have two vectors here, one of them indicating how you are rowing or how the wind is blowing you or something. That is with respect to the water that is surrounding you. The water itself could be moving. So this is velocity of a boat with respect to water. This is water with respect to land. Now what we are after is description of both with respect to land. How do you do that? Well, we have the concept of vector addition in physics, that if you have two directions, two velocities, and then you want to add them, the way you add them is to make a so-called parallelogram. So you can go to the tip of one of these vectors and draw a vector parallel to the other one. Or you could have come to the tip of this one and draw a vector parallel to the blue one. Both of them end up at the same spot. That spot indicates where your overall velocity is going to be with respect to land. So this is velocity of boat with respect to land. Same thing could happen if you are trying to describe movement of an airplane. If this was an airplane, you can maneuver it with respect to the air that is around you. So that gives you one velocity. But that air could be moving with respect to Earth. So if you want to find out how the airplane is moving with respect to Earth, you have to add up these two velocities. How do you add two velocities? You have the law of addition of vectors. You draw both of the vectors starting from some point and complete a parallelogram with these two sides. The diagonal of that parallelogram is going to be your resultant velocity. So this is referred to sometimes as a resultant velocity. Same principle applies when you are applying two forces to an object. If there are two forces acting on an object, for example, you might have a magnetic object that is being pulled down because of the gravitation of Earth, and perhaps you might have some other magnet that is trying to pull or push it in some direction. So you might have one force and then a second force from different sources. How does this object react? This object reacts as if the resultant of these two forces were applying to it. How do you calculate the resultant? You complete a parallelogram, you draw the diagonal of that parallelogram, and then this is going to be the resultant force. Sometimes you don't need to draw the entire parallelogram. So I could have done it like this, like I could have drawn that blue one indicating that velocity of the body of water. Then I can go ahead and draw that green one tail of it starts at the head of this one, and then I go. How do I draw it? I draw it parallel to the other one. So this is actually a copy of the other velocity. Okay, so now I have two velocities drawn kind of head to tail. Then starting from the very first tail to the very last head, I will have my resultant. So simply this is like half of this picture. We have just drawn that one. We didn't draw the entire parallelogram, but you realize it's really the same thing. I could have drawn the green one here and then the blue one here, and I end up at the same spot. Okay, so it is possible to handle vectors by just drawing and talking about it in a graphical sense. That's going to be a little bit uncomfortable for us to use because it would be hard to get numbers out of this. So we are going to adopt a different way of describing vectors, which is more amenable to calculations, and we are going to suffer from the fact that we are going to lose the pictures. The easy access to the pictures is going to be lost. So we are going to go ahead and describe we start with our standard Cartesian coordinate system. So the same XY coordinate system you started using back in 8th grade. We go back there. Now, suppose you start at the origin, you go two steps to the right and one step up. In algebra classes, you would have referred to this as a point with coordinate 2 and 1. That was great. Now you can come and say, well, I can describe this vector, which is made out of these two components, 2 horizontal and 1 vertical, by a notation similar to that. Some places they use this notation. Sometimes they use this notation with the bracket. And there would still be some other notations to be used. The alternative notation that we have is going to kind of spell out that we are taking 2 steps in a certain direction and 1 step in the other one. What we are going to do, we are going to formalize the concept of a step. You say step to the right, we are going to call that I. Step up, we are going to call that J. So I really corresponds to going from the origin to the point with the coordinate 1 and 0, and J is starting at the origin and going to the point with the coordinates 0 and 1. Now 2 and 1, the vector with component 2 and 1, is made out of 2I plus 1J, because I took 2 steps to the right and 1 step up. Notice I can write this as 2 times. I was 1, 0, simply a step to the right. J was 0, 1. Well, how do we multiply a vector with a number? You simply multiply each component of it by that number. So 1 times that is just. Now how do I add 2 vectors? Instead of going through that difficulty that we had there, that you had to draw a parallelogram and such, here we get a little bit of a reprieve. Life is easy. You just add up the corresponding components, exactly like you did with respect to matrices. So a lot of things that we do here is borrowed from the notation that we had with respect to matrices. Okay, so once again, a point that back in algebra or geometry was given by a pair of numbers could now be thought of as a vector. We start the vectors from the origin, point 0, 0, going to that place, and we use bracket to indicate the vector. We separate the elements of this list by commas. Alternate notation is to come and say, okay, these are steps, we are going to call them I and J. This is a standard. These are called unit vectors. in different fields they call them different things. We are going to talk about that later. But right now, since you took 2 steps to the right, so you have 2i, 1 step up, so you have 1j. This was same as I, this is same as j. And when you simplify it, you come back to this notation that we started from beginning. Okay, let's go practice some arithmetic with vectors. What do you mean by arithmetic? Well, as usual, we have addition, subtraction, multiplication, and division. I'm going to put a question mark underneath this to see how we can make sense of it. Of course, we had other things in mathematics. We have powers and compositions and such. We might even put more question marks under this until we explain if they make any sense at all. Okay, to get started, I go ahead and start with some vectors. Suppose I have vector with coordinate 3, 5, and I have another vector with coordinates 1 and 2. Question is, what is a plus b? We are practicing addition. So, not a very big surprise that this is 4, 7. So, handling this in coordinates is, in components, is very easy. Handling it in picture or graphical representation of same thing is not as easy to follow. But let's just practice here. 3 5s, we said that simply means 3 steps to the right, and then 5 steps up. I went a little bit too much here. So this is supposed to be let me change my mind so that my picture will come out a little bit better than what I have here. So let me change it to 2, 1, so it'll be 5 and 6, so that things don't run into each other. 2, 1. This is supposed to be my vector b. Adding them on a picture, I was supposed to either bring the red one up here or bring the green one to the right. Yeah, they do end up at the same spot, and that spot is what we are after, which is, okay, so this thing is a plus b. Well, you can follow that if you had gone 3 steps to the right and then you go 2 more steps to the right, that of course you have gone 5 steps to the right. And if you had gone 5 steps up and then b takes you 1 more step up, by that time you are 6 units above the x-axis. Well, what if you wanted to subtract? Again, do what comes naturally. You are subtracting, so this is 1 and 4. Let's try to understand subtraction in picture. First of all, what do you think we mean by minus b? Negative of a vector, you simply make each component negative. But what does that mean in a picture? If I have some vector with component 2 and 1, how would we describe negative b? Well, it's negative 2 and negative 1. So what is a verbal description of negative b? It's same magnitude or same size, but opposite direction. What you expect from that. So if you had, let me go ahead and draw my my b was red. Now when you say a minus b, you really mean a plus minus b. your A was the original A. So let me just try to copy that. If you wanted to add A and B, well, you would have made a parallelogram here, and that would have been done. If you want to subtract B from A, it is as if you are adding negative of B to A. So as if you had an opposite force to the original force, and then you are taking the resultant of these two. How do you take the resultant? Well, like you take this you take a vector which is opposite to the vector B, you back up. So we say we back up by as much as vector B from the tip of A, and the resultant now is going to be whatever this thing is. So this is A minus B. And then it doesn't come as a big surprise that if A, you had gone 3 units up, B brings you 2 units. Let me say that again. With the vector A, we had gone 3 units to the right. B, backing on B, you're going to lose 2 of those 2 units. So you have gone to the right by just 1 unit. A took you up 5 units. Minus B is going to bring you back 1 unit. So A minus B is going to be 1 minus 1 and 4. So let's practice this thing again. If I have a vector A and the vector B, and I'm asked to graph A minus B, that's what we want to graph. From tip of A, I graph minus B. And then this is going to be A minus B. Here's an alternate way of looking at these things. Here's A again. Minus B, I can simply exchange the heads and tails of it. That is, if this was the layout of the B, I can start from here and then go in the opposite direction. This is going to become minus B. So I have minus B plus A. The resultant of these two is just going to be, okay, so we start from the tail, go to the final end. This is going to be A minus B. This is drawn here, this one is drawn there, but they are actually the same vectors as far as we are concerned, same quantity. So here is addition and subtraction of vectors. It with components is straightforward. Graphing of it, you need to practice a little bit to see what's actually going on, and after a few practice problems, this is going to be natural to you as well. Now, to more complicated things. How about multiplication? You remember this was the beginning of our time when we were dealing with matrices, so it's not going to come as a surprise to you that with vectors also we are going to have a bit of a hiccup with respect to what you mean by multiplication. Let's start with the easiest one. Well, what do you mean by multiplying a number with a matrix, with a vector? Well, this is not hard to visualize what's going on. If you have a quantity that has a magnitude and direction, doubling it simply means what? Doubling the magnitude of it and keeping the direction exactly as it was. So if this was your A, then 2A is not going to come out as a major surprise. This is also another way of describing, A plus A. So if you have a vector A and then you copy it next to itself with another A, well, then you have 2A. So this multiplication is trivial. How should we talk about this multiplication? This is a number, this is a vector. We said our numbers are now being given a fancy name. They're called scalar. This is our vector. So scalar vector multiplication is no surprise. It's just a title is a mouthful, but so what? We have to be careful with if our scalar is negative. What does minus 3a mean? So if I have, yes, very, very good. So negative means flip it over. So we have to flip it over. So this is going to be negative a, and then you copy it 3 times. So perhaps this is negative 3a. So multiplication by negative scalar, you lose your, or you reverse your direction. So you that negative gives a command reverse direction, triple. So that 3 gives a command triple who, triple the original you got, you just triple that. Okay, that becomes the end of easy kind of operations we can do with vectors. Anything past this point is going to be a little bit more complicated. Let's see what we have so far. Let's just do a quick review of certain so-called axioms of field. Let's see. The word field here, not to be confused with those terminology we were using in physics. We're not talking about gravitational field or magnetic field or something. It's just an expression they have in mathematics. So we have things we call vectors, and we have other things we call scalars. So let's typical letter that we are going to use for vectors are going to be U, V, W, and such. Typical letters we are going to use for scalars going to be like A, B, C, or T, S, T, things. Okay, we have 2 kind of creatures, vectors and scalars. We are kind of arranging a sort of a game for us, playing with these symbols, like kind of a board game. What kind of things do we expect from these things to satisfy? First of all, what do you think is a 0 vector? Whatever component it's going to have is going to be 0. So 0 vector is the only vector that doesn't have a direction. All of its components is 0. So its magnitude is also 0. What do you expect is going to happen if you add that to any vector? So it's not going to make any difference, of course. Now, if you had 2 vectors and you were adding them in 2 different styles, what would you expect to happen? That addition of 2 vectors is going to be the same. So if you have one vector v and another vector w, whatever you mean by v plus w, it doesn't matter in which order you are adding them. V plus w or w plus v, both of them takes you to the same spot. So this is v plus w. So we have the law for commutativity. And similar laws that you have seen back in your Algebra 1, many of them are applicable to this situation as well. So, for example, if I have 3 vectors to be added, what would be my first worry? My first worry would be, okay, which 2 of them are you going to add first? And thankfully, it doesn't matter how you go about it, you always end up with the same answer. What did you call this thing back in algebra class? Now, corresponding to each vector, there is another one which we call the negative of that vector. That if you add that to the original, what do you get? This is this 0 vector. So every vector has an opposite. Okay, so this is sometimes called additive inverse. Okay, so they have these fancy names to describe the tools of the trade. So this is the identity element of addition. If you are interested in going further in math, these things are going to be important, but if you're looking at the application, probably terminology is not going to be all that important or exciting. Okay, these are some of the basic rules as far as you are concerned with addition. Well, what kind of multiplication do we have? We are not going to have any multiplication between two of these guys. Rather, we are just going to have multiplication with one of these and one of those. Scalar vector multiplication, that's going to be the very first. So what do you expect to happen if I take number 1 and multiply by vector v? Just go back to what you had. So what else could happen? This is 1 times v, just v. If I have several scalars to be multiplied and then multiplied by a vector, question that comes up to mind is that what are you going to do first? And the answer is it's not going to make any difference. That is, if you multiply your scalars first, then you multiply by vector, you get certain thing. If you take that vector, multiply with one of these scalars first, and then multiply by the second one next, we expect to get the same answer. So we have something looking like this associativity property of multiplication in this case. What if you have sum of two numbers multiplied by vector, like 2 plus 3 times vector v? What other way could you represent this? Yeah, a times v plus b times v. What did you call this kind of things back in 9th grade? Distributive property. So long as you have a multiplication of a vector with a scalar, then rules of algebra that you have are still applicable, and there are no major surprises. What is, for the time being, is still left as a question mark is there any kind of multiplication of a vector with another vector? Okay, so that is going to be something new. Multiplication, so we are going to call vector multiplication. So again, scalar times a vector, that's no big surprise. It's just doubling something or tripling something. Scalar times a vector. So scalar times vector, that is not a big news to write home about. Scalar times scalar, well, that's what you have been doing in elementary school, just 5 times 3 and 7 times 9, that multiplication table you learned. That was fancy name for it would be scalar. You have now scalar vector, so that is not a big deal either. Big deal starts at vector multiplication, and we are going to see that there are 2 types of vector multiplication. One of them results in and the other one results in a vector. This one is represented like this. You write the name of one vector, you will have one big dot, solid dot there, and the name of the second vector. Then there is another kind of multiplication that you have to define. You write the name of the first one, then you borrow the other notation from elementary school, that cross notation for multiplication, and then you have the name of your second vector. Depending on what field you are going to study in, they might give these things different kind of names. This one might be called scalar multiplication, as we called it, and this one is called the vector multiplication, as we called it. Those of you who have taken a physics class or have taken calculus 3 or something, you recognize this by some different name. What do you call it? Yeah, this is called the dot product. This one is called what? Cross product. Before we go any further, let me just give some brief meaning attached to these things, so that we have a little bit of motivation, that we are not just making things, fabricating stuff. The dot product, the very first application of dot product that you see in physics or statics or something is what? Yes, the way it's going to be done, yeah, we refer to this kind of multiplication when we talked about matrix. Matrix multiplication is essentially the same thing. Over there also I talked about an application in physics. If you have a force and displacement. So you have a force being applied to an object while the object is being displaced by a certain vector. There is a very important notion attached to F dot D. What did we call it? What is it called in physics? Force times displacement. So you have a force, and this is displacement. Sometimes they put an arrow on top of these things so that you recognize them as a vector. Somebody said it, what? It's a work. Okay, simplest kind of work that you know is direct lifting of an object. So I have this object in my hand, I'm lifting it up. So if you have some object that is having some weight, and then you apply a force to counter that weight, so this is a force that you are applying it, and then you move this object by a certain distance. So you have force applying on this, and you are lifting it, and then what? Well, you expect to be paid. Is that right? It's okay, I've done this much work. Why? Because the object that is now up here has potential energy stored in it. If you release this, it falls down. It can create energy for you. You can do stuff with it. So I've done some work for you, pay me and such. So F times D, it's the work, a concept of work that you have in physics that is of this nature. Now, there is another multiplication that is done in this style. Perhaps over there, instead of D, let me use R. Does that remind you of anything in your physics class or cross product? Yeah, I'm looking for the physical notion of this thing. Think about a steering wheel or something, or one of those tools they use for opening up what? What is that called? The T thing that, yes, a torque that you use for opening the bolts on your tires and something. So here you have some force. And you have some distance from the center of rotation. Now the applicable quantity here is F cross R, and that measures, somebody said it, what is it? Torque. Is that how you write it? I forgot. So when you are studying rotational motion, like you're having a steering wheel in your hand and you're turning it, or you're using a kind of wrench of that style, you're trying to open something, the quantity you want to measure is F cross R. Now here, conveniently, they are perpendicular to each other, but they don't have to be. So you could have some R and some F, the question is, well, what is F cross R? You are going to use this concept when you're talking about stability of objects. You want to make sure something is stable. You are going to also make major use of this thing in electromagnetism. Cross product comes in big time over there. So both of these things have their roots in application. We want to go ahead and describe this one first, the scalar or dot product. Very first thing we can explain is what do we mean by dot product of a vector by itself. Dot product of a vector by itself. So now you have a vector dotted with a copy of itself. This is going to be square of magnitude or length of vector v. So v dot v is going to be, in some sense, square of the vector, but we are not going to have the concept of squaring and cubing of vectors. Rather, you take a vector, you find the length of it. The length of it is indicated by putting it in absolute value bars, and then you can raise it to any power you want. So we have this notation of v in absolute value that is going to be the length of vector v. Let's go after some very simple vectors and see what is their length. Suppose I have a vector with coordinates 3 and 4. I ask what's the length of it. To get started, we go after our intuition in geometry. So this is vector which has 3 to the right and 4 up. This is our vector v. So what's the reasonable notion of length for this? This is 3, this is 4. Very first geometry class tells you what? The 5. That would be one reasonable notion of length for a vector is going to be just what we introduced. So how did you get that? So I took a square root of the two components, added up. That became square root of 25, and I got a 5. So for the time being, if I have a vector with components a and b, the length of that vector is going to be simply what you did in the geometry class. Sometimes this is referred to as the Pythagorean length because that's a length that's used in geometry a lot. Okay, we have a lot more to say about dot products. This was just the very beginning of it. What you want to do is take a look at problems of 3.1. As I mentioned, this is going to be a lengthy section. You want to do a bit of a practice. Except for the notion of span that I need to explain, you can handle problems from from 1 through 30, but we are going to explain the notion of span in the next lecture.